Okay, welcome back. As I say, I'll be done by 9. Okay, so yeah, I'm going to sketch the microstructure. Okay. So this is no load. So the round stuff are bainite. Okay. And then you have your no, not bainite, sorry. Your martensite. Now this is at room temperature, yeah. Then you have your round stuff. Retain austenite. Okay. Then you have your diamonds. Microstructure of trip steel. We're still on trip. Okay. And then you have your diamond. And then the rest up there, right? Okay. So this is at room temperature, no load. So now once we induce stretching or bending or whatever, the original martensite are still there. Right, the original martensite are still there. And then what will happen is the diamonds are still there. No change. Okay, one. So you have some diamonds here and here. Okay. Now, all this that used to be retained austenite becomes what? Martensite. So these are the retained austenite transform to martensite. All right, so that's why the percentage of martensite changes, okay, as you stretch or bend this material. So as mentioned before in the table that I've written before, but I'll put in words. So in trip steel, okay, in trip steel, retained austenite is thermally stabilized at room temperature with, you have to use these three, okay? Silicon, manganese, and aluminum. Okay, you cannot do one or without the other. Okay, they stabilize it. Now, when we say thermally stabilized, means because of heat. Upon stretching or impact anything, it will what? It will transform. Okay. So the superior, as you can see from here, the superior behavior, okay, strain hardening behavior behavior is due to transformation.
Sorry, Eugene, I thought you said austenite was thermally unstable before the break.
Yeah, but it's thermally stabilized by adding this. It's unstable at room temperature, but you stabilize it with silicon, manganese, and aluminum. Does it make sense? Without these three, it's unstable. Okay, so transform. So the superior strength is due to the transformation of retained austenite to martensite, as you can see. Okay. So over here, okay, is about the crossover is about 0.1%, okay, approximately, or to 0.2% of strain, okay. So note, okay, so the plastic strain induced during manufacturing should be in the range of 0.1 to 0.2. Okay, you go more than that, okay, you can go higher. I'm not saying that you can go higher, but it's going to get more and more and more difficult. Okay, as you can see how the material is transforming as you strain more transform to martensite. So this is the good thing about this material. Remember, we choose this material for the rear end of the car, yes or no? Right, the rear side pillar, yes or no, or member, right? When it crash, it hardens because of what? Martensite what? Formation. Okay, so now we understand the material. Okay, let's see what is this project all about, or how I help my platinum client, okay, design a product. Okay, so I did not design the whole product. Okay, my part is to tell them how the material behave and what consideration has to be made to design for manufacturability. Okay. So this is the design stage. As I say, I was not in front of the CAD drawing, whatever. Yes, sir. When I alter body shape, pull a frame after, are they technically making it stronger? Yeah. So if the material structure, if the material has been deformed already, so let's say let's say the material crash, okay, and then it strains up. It did not fracture, okay. It make it harder, so it reached this point already, right? So that's why when upon impact, some structures are difficult to pull back. Okay, so pulling back from here takes a lot of energy. Okay, the problem is this. The only time it can absorb more energy is here. So energy has been expanded already. It's been hardened already. So less energy. That's why when something is harder, it becomes more what? Brittle. Right. That's a really, really good question. Okay. So now after impact, so you straighten it. Fine. You could straighten it. Okay. And the problem now is this. Upon your next impact, right? I'm not saying that this is a true value. This is a trend. The material cannot absorb so much more energy anymore. It might break because this is the energy that it can, the energy that it can absorb more. Does that make sense to you, Ryan? Ryan? It's a good question, okay? It's really, really a good. That's why cars that has been through structure damage, try to avoid them. Okay, I'm not saying don't buy. Okay, try to avoid them. That's why their costs are so much lower. Structure, okay, structure is the critical part. Okay, so if you buy a car, I'm not saying that cars has been an accident is bad. As long as you're careful, I will buy a car that's accident that is like 10,000 cheaper. Okay, just be careful when you drive. Okay, that's all I can say. Okay, sustainability, right? You tend to buy used. Okay, let's go into our case study. So what we have is, again, we have a material with so the original. So this is designed for manufacture. So you know how trip works already, okay? What trip 800 are. So we have material with a length, I call it CN, okay? And this is our raw material, okay? Raw material. Okay, raw material. So the thickness of the plate can change. Okay. So the next one is the design. Okay, design requirement of finished product. So for simplicity's sake, okay, it's going to be bent into this shape. Okay, I know it's out of proportion. I can see that. Okay, so the outer surface dimension